Welcome to our weekend recording of the February 14th and 15th in the year 2026 as we're on our way today. We've heard from Anne that she will be celebrating the Chinese New Year and won't be joining us. We've heard from Joe that he'll be a little bit beyond the appointed time. And we're waiting to hear back from Richard. I sent him a text and Manu will show up when he shows up. Lee, if you're ready to go, how are you feeling? No, you're still eating something. So you finish what you're eating. And Fred, how are you feeling? And what do you anticipate getting out of today's call?
I'm feeling pretty good. Thank you very much. Glad to be on the call. I was up early to watch Scotland beat England and Ireland nearly get beaten by Italy in rugby. And tonight we have France hopefully beating Wales. That's a Six Nations tournament, and this is the best tournament in the world, rugby.
Cool.
Um, I spent my Valentine with Susskind, Leonard, the physicist, and I've heard saying that you guys don't want to hear. So that's all I'm going to say about that. And my expectation today is to learn a little bit something. So Lee, how are you feeling today, and what is your desired takeaway?
It was the most wonderful day, Valentine. We went to see Machu Picchu. In what was the way that we watched it, Steve? Oh, virtual reality. First time I'd ever had one of those headsets on my head. And I thought what the gentleman asked first was, is anyone scared of heights? Of course, we were going to be climbing up the high mountains. And I have been a fireman for 5 years and slid down hoses off of the third floor. So I never thought that I'd be a little wobbly with height. But it was a little more than I could handle. I was dizzy, totally dizzy, but it was fun. What I was saying, Richard, was I went to see Machu Picchu, Picchu, um, with virtual reality. And the height of where we had to go up, you had to step on rocks, and then they would lift you up to the height of where they were taking us, to the top of the mountains and into the clouds, and the rocks were flying around in the heavens, which was beyond me. Never thought that rocks would be floating in the air unless it was in a cartoon of some kind. But it was fun. It was really well. And I'm looking forward to tonight. Have no idea what we're going to be doing, but I'm excited. Richard, how are you? And what would you like to take out of tonight?
I'm pretty good. And even better now that you've talked about your virtual trip to Machu Picchu. Um, I made that trip in person in the early 90s. And yeah, that was quite an experience to take the train and down into that part of the of Peru, and then being able to get up into that whole ancient area. Wow. Um, And well, I'm really wanting to learn more and more about holism, and um, and the reason I say that is that I just got a new book from the Perry Center, which is a rewrite or an update of a book that was written 40 years ago called The Looking Glass Universe. And the subtitle of that book back then was The Emergent Science of Wholeness. Um, and one of the original authors, John Briggs, who is an American, and he's a poet and an artist, had authored the first book with David Peat, who was an atomic physicist. So it's an interesting combination of authors. And the third, or the this last one, the update one, still has John Briggs involved. David Peat is deceased some years ago, and a student of theirs, Jonathan Alday, is involved. And what's really exciting as I've skimmed through the book, I'm sort of jumping all over the place. John Alday talked about when he got involved with this kind of science, and it was 40 years ago. Well, he talked about in 1989. Um, and he finished off his little introduction, his preface, by saying that what we thought was the emerging science of wholeness 40 years ago, it's still emerging. It hasn't emerged yet. And hopefully someday it will. And that gave me a lot of confidence because I've been beginning to feel that Fuller's ideas and thinking are well over 40 years, and they're still not in the mainstream. And it's like almost ready to give up and say, well, maybe it never will. But this new book has given me the encouragement to think that people like engaged in our kinds of dialogues and others like it um, are still sort of um, the lever, if you want, or the catalyst to help with the emergence of holistic science. And my own sort of proof of this slowness is that in that same year, 1989, I have discovered a paper that a student wrote, a Bachelor of Social Work student, who wrote about it's time for my discipline, our discipline, to get engaged with the quantum um, understanding of things. In fact, she named her paper "A Quantum Leap is Required in Social Work." And when I read that paper recently, I think, like John Alday said, I could put that in a contemporary sort of package, and it would still be leading edge. We're still in the process of becoming. So that's kind of where I'm sitting today in terms of how I'm feeling, and also it is giving me that sense of encouragement and support that we should continue these kinds of dialogues because the science of wholeness is yet to be, but it's not gone or lost or forgotten. It's going to be at some point, and we're going to be part of the seeds that are encouraging that emergence. So, yeah. So, Manu, welcome, and how are you feeling, and what's your wishes, intentions, what you'd like to get out of today?
Good morning first. I'm feeling good. Again, I got into the midst of the sharings, and yours seems to be very interesting, Richard. I enjoy what Steve sent over the week. And well, let's continue. I think that we are on the good path to understanding things and to applying, because you understand better, you should be able to apply it better because you make less mistakes of assumptions and things like that, and go for things that are useful and that help your environment and yourself. So that's my hope takeaway from this. Who's left? Is Steve or Lee?
It is I.
Steve, how do you feel? What do you expect?
Well, I'm feeling pretty good. I didn't get much sleep last night. I got about 5 hours and 20 minutes in it. I tried to take a nap before today's call and I didn't get it. I got a little rest, but boy, I'm just feeling a little bit groggy. I'm enchanted by this whole concept of wholeness, and it really does. I, I sent out a couple of videos over the weekend. Fred's response to one of my videos, well, it has really great graphics and it has triangles. It must be true. Yeah, I'm still chuckling about that because, you know, and now with AI, I'll tell you, there is really amazing graphics on every dadgum thing, and it's gonna be harder and harder to tell any kind of truth from anything. And in fact, I was listening to the All In podcast tonight, and they talked about how that businesses using AI run the jeopardy that all the proprietary information gets out on the AI and it suddenly becomes public domain. So any business that wants to maintain propriety, maintain its franchise, maintain its copyrights, has to put everything on a private network and engage in special protocol. Otherwise, everything they do is out there, and any Tom, Dick, or Harry can pick it up and roll on it and not have any idea that they're stealing something from, from Thiokol, or whatever. So that's interesting. Richard talked about in the 60s trying to make everything whole. I'm really, even with the graphics, I find I don't believe everything I see on the internet, even with the beautiful graphics and the triangles. But it would really be nice. And I hear people like Donald Huffman talking about the amplituhedron, which is supposed to be some kind of cosmic structure that's underneath that's underneath the Planck scale, and that's below the Planck scale and above the Planck scale. And so there are these fringes all around that keep talking about things like Bucky talks about, and it'd be nice to see them hooked together. And Richard, your comment that the paper in 1960 could be written today in 2025 or 2026, when are we going to take the quantum leap? I can remember back in the 50s, we talked about aerodynamic cars, and I'm starting to see some of those designs now, and that was that's 60 years ago, but I remember being all involved with building model cars and talking about wind efficiency and seeing smooth lines and stuff. And now it's happening everywhere. So I don't know, human beings are the craziest people on the planet. I'm looking forward to reading this and to getting a little bit of knowledge. And I find out that I get this little bit of knowledge, and 5 years from now, it'll make sense to me in more than it does now. So I'm hoping that to plant some seeds here and there. I'm really grateful that everybody's here. And I'm excited about planting some seeds. There's a chat here. I'm going to check out the chat. Aha, lag. Absolutely right. 60 years to get a car that looks nice. Anyway, I thought we'd start our reading on page, I think we got to page 240. However, if we start on page 239 at the section heading least common denominator, we'll pick up the introductory wording and be able to jump into the topic, I think, a little bit better. So we'll go from there. We're anticipating.
What page do you say?
We're going to start on page 239. For those who are interested, we're going to start just below the graphic figure 14-8.
Okay.
We're going to start just below that graphic. And I'm going to share my machine here. Here we go. And I figure if we start with least common denominator, we'll have the least amount of confusion. All right. I'll start reading and then we'll pick up. Hopefully Joe will show up. He likes to read a little bit too. So we'll see how that goes. And I'm finding that I've got to use a little, I got to open this up a little bit more over here. Okay, good. Least common denominator. The spherical icosahedron, okay, good. The spherical icosahedron divides the surface of a sphere into greatest number of completely regular domains with both equal arc lengths and equal surface angles. We can therefore subdivide one of these symmetrical triangles to find the least common denominator of surface unity, in which, in much the same way, we isolated A and B modules, period. Each triangle is split into 6 equal parts by perpendicular bisectors to obtain a final non-symmetrically divisible unit, figure 14-9A. That was 14-8, so this is 14-9A. The result is 120 asymmetrical triangles, 60 positive and 60 negatives. The maximum number of equivalent domains on the surface of a sphere. These perpendicular bisectors are the icosahedron's 15 great circles. So, since we've read this before, we had a big discussion about positive and negative triangles. So I'm going to just share, and you guys can correct me. A positive triangle points in one direction, and a negative triangle points in the other direction. Or a positive triangle has a base on one side, and a negative triangle has the base on the opposite side. That's what makes it positive and negative. And it can be sideways, but I usually like to think of it up and down. It's easier for me to see. Also, I was just discussing with Fred before the call, I figured out what a least common denominator is relative to a mite. What we're seeing right here is this triangle of the icosahedron is broken into, is bisected until we end up with a whole bunch of different sized triangles. And when I take this one major triangle and bisect it in this fashion, I end up with unequal triangles, and these are the least common denominators if I understand it correctly. Does anybody want to comment on what I just said?
I think this is wonderful that you say that, because this refers back to conversation we had probably two months and a half ago, probably before Christmas, where when we talked about the quanta and the mite, we talked about we divide symmetrically until it's no more possible to divide, and you had a difficulty to see that. So I think this relates to that, and you've made a connection, and that's wonderful.
Yeah. When I bisect it here, I end up with a right angle here and a right angle here. When I start doing these, there are no right angles, wherever there's no right angles. So over here, I've got all of these lowest common denominators. That's what I'm getting. There's no commonality other than they match each other on the opposite side of the bisection. So I think the more I talk, the worse I understand it, but that's what I'm getting out of it so far. Thank you, Fred, for at least reinforcing part of what I came to. Any other comments or questions on what we're seeing here? Figure 14.9, maximum of 120 equivalent domains, or LCDs. Imagine that some number of hypothetical creatures are to inhabit the surface of a large sphere, and it is considered necessary that each one sit in the middle of an identical plot. The consequence of this stipulation is that no more than 120 creatures can sit on a sphere, no matter how large it is, because these relationships stay the same. They just get bigger and bigger, or smaller and smaller. It seems that we should be able to accommodate as many creatures as we want. But that's not true. However, the unyielding law of symmetry limit the population to the unexpectedly low number of 120. So no matter how big these spheres are, the least common denominator is going to be a part that is 120th. We go back to the 31 great circle diagram to observe the 120 triangles in context. These asymmetrical triangles are true LCD units. Any one of them contains all the geometric information necessary to construct the entire pattern. Wow. That sounds like a fractal to me, Fred. If it has all the information needed to reconstruct the entire pattern, isn't that a fractal? This, I don't answer it yet. That was rhetorical. You have a chance to think. Let's finish the paragraph. This is an important factor in the development of geodesic domes, as we will see in the next chapter, which discusses the relationship of great circles to geodesic domes. I'm going to pause right there. What do you think? If I have an entity that has all the information necessary to construct the entire pattern, isn't that a fractal?
Well, does it
Isn't that
scale?
also holographic?
So Richard
Steve,
suggests it's holographic. Go ahead, Fred.
does it scale? Do you have the same pattern at all scales?
So that's different than a fractal. An LCD is at all scales and a fractal is at a certain scale, a fixed scale. Is that what you're saying?
No, what I'm saying is that this LCD is at only one scale. No matter the size of the sphere.
Oh, I see. No matter the size of the field, we're locked into 120.
No. Listen to me, because this is ambiguous here. Any sphere, you can divide it in 120 equal parts on a surface. That's all. That is,
Okay.
you cannot go deeper, go closer. You cannot scale in and zoom in or zoom out and still have the same pattern. It is not a fractal.
Yeah. He said this, that no matter how big your sphere is, if you're going to have creatures with identical sized plots, 120 is your maximum, no matter how big your sphere is.
Yes.
Yeah.
If it was a fractal, you could
I could have more. Gotcha.
Keep subdividing it.
Okay, good. And Fred, Manu, you've got your hand up patiently. How are you doing? What you got to share here? You're on mute, Manu.
Okay. I wanted to share another way of getting there, I think, easier. Can I share it?
Yeah, you have the floor, sir.
Okay. You remember the circle and the hexagon and the pentagon in the circle. We discussed this last week or 2 weeks ago when we were talking about the boundary.
Yeah, Fred gave us a really good dynamic model of the pentagon turning around inside the sphere inside the hexagon.
All right. If you imagine that representation, the hexagon has 6 great circles dividing equally the 360 degrees of a circle. What is the angle of each of the sectors is 60 degrees.
Yeah, 6 times 60 is 360.
Yeah. The angle of the pentagon has 5 dividing the same. The angle of the pentagon sector is 72 degrees. What is the maximum common denominator between 60 and 72 degrees? Is 12 degrees.
12.
360, 12 degrees, or for that matter, 720 to divide the two, everything. You just say 720 divided by 12 is 60. 360 degrees divided by 12 is 30. If you're talking about, say, the one circle in 12 degrees, you have 30. That is 30 sectors of 12 degrees. And then you have the equator that divide also that sphere that way into two. So that is 31 great circle. Do we get there? If I take 360 degrees and I divide by sectors of 12 degrees, I have 30 sectors that way. If I section it at the equator in half, then I have 30, no, not 30 sectors, 30 great circles. And then plus equator is 31 great circles that divide my spheres, my sphere. If you divide then that way, you have exactly the figure that you have in, oh no, not that way. You have 30 this way, like that. And then you have the 60 degrees where you have 3 that way, that is 60. And then you divide by 2, again, you have 120. Let me explain it simpler. You have a sectors of 12 degrees, like this, 12 degrees. You take a circle, you divide that by 12 degrees. The circle is 360 degrees. Divide by 12 is 30. You take that 30, there is the north and the south of a 30. That is one, how will I call it? You divide it by the equator like this, and you divide it again like that. You have 120 sectors, all centered at the center of a triangle. Did it make it complicated? I want the feedback here. Did it make it complicated or easier?
I get about half of what you said, to tell you the truth.
It's
I'm really
correct.
good. I'm really good with the 60, with the hexagon at 60 degrees times 6 is 360. And I'm really good with the pentagon at 72 degrees times 5 is 360. And I'm really good with taking the 360 and dividing it by 12 to get 30. But I'm not sure how you get to, when you start bringing in equators, I'm not sure what that's all about.
When I start bringing the, yes?
So plus the angles on the surface of a sphere are incorrect. You're taking angles on a flat plane and you're trying to transcribe them on the sphere, on the surface of a sphere, but this is incorrect. The angles don't transcribe.
Or it is incorrect to you because we don't see that they all go through the centers. If I take a sphere like this.
We talk about great circles and you're talking about the angles of the intersection of great circles. Am I correct?
No, he's talking
No,
about
I
North
didn't
Pole
talk
to
about
South
angle
Pole.
intersection of a greater circle. I'm
Well,
talking
then you
about
need-
great
then-
circle,
then-
all
then-
passing
then
through.
you need, okay, then you need to clarify what you're talking about because doing this with angles and all that, it's really
But
not helpful.
yeah,
So
okay.
can we see something?
Okay. Listen again attentively. A sphere has 720 degrees. Do we agree to that?
A sphere of 720.
Yes.
For what?
Um,
What are you measuring?
Okay, a sphere can be represented by one circle horizontal and another circle that is perpendicular to that circle.
And you add the two together and you get 720.
Okay? So if they divide the first circle in 30 parts by dividing 360 in 12 sectors, I have 30 parts. Do we agree to that? I have 30 arcs.
Yes.
Okay. I take the same stuff on the circle that is perpendicular. I divide it again by 12. I have another 30 parts. So I have 60. Do you get that?
Okay.
No,
If
I don't
now,
get it. You have, it's not in the same plane. So you have 60 what? 60 sectors on two different planes.
On two different planes. But that comprises a sphere.
yeah.
How does that go to a sphere? Because if you rotate that one like this and the other one like that, without going into too many calculations, but you're going with all the intersections. If let's say you have rays like on a bicycle, like on a bicycle wheel. If you do this with one, that with the other one, and this cuts through butter, you're going to get 900 small shapes of butter cut out of it.
Somehow we go from the 2D plane though to a 3D plane.
It is exactly what you have on figure 1410. If you take
1410?
figure 1410, yes. That's exactly what I'm describing.
Yeah, but what we have in 1410 is a surface of the sphere. You say we're not talking about the surface.
Fred, let me repeat
Yes?
again.
No,
If I
don't
take
repeat. Explain. If you repeat, I'm going to get exactly the same thing. Just make clear what you want to say.
I'm
But
making it clear.
repeating is not helpful.
I take a sphere.
I understood all the words. I just don't understand what you're
Okay,
talking about.
you see on that sphere, you see on this sphere here, do you see those lines that are bold?
Yes, the bold lines here.
Yes, I see. Yes, I see them. Then
How many are there?
these
Hold on. Yes. How many are there?
31? I don't know.
No,
31,
the
No,
bold one.
five.
the thick lines, the thick lines.
How many? 3.
Now, one going around here, one going around here, and one going
Okay, you
around
have
here.
3. Then
Okay. If you take those 3, and then you consider the others that are in finer lines.
what?
We consider the other lines that are finer lines. Is that what you're
The
saying?
final line, yes.
Yes. And the finer lines, according to the stuff, the difference between the bold and the next one, the arc on it, and the next finer, the first bold and the finer, is 12 degrees. That's all I'm saying. And the
So
whole of that.
so we're talking about the intersections of those lines on the surface of the sphere. Or you're talking about the intersection of the planes at the center of the planes that define the great circle by intersecting with the sphere. Are we talking about the plane, or are we talking about the surface of the line on the surface of the sphere?
I'm talking about the surface of a sphere and how that surface is divided into 120 sectors of equal surface. That's what it is. That's what we have described all the way in that text.
Yes, but my problem is I don't understand how you get from 30 sectors of 12 degrees on two perpendicular planes, cutting a circle, cutting two circles, but on two perpendicular planes. How do you get that into a sphere that's 720 degrees? This I don't understand.
It's visible there, isn't it? You have 3 bolts. One of the bolts is the equator. You have 2, and one is the equator. And everything is a final line.
By definition, all 3 of them are equators. on a sphere?
Depending on where your pole is. Depending where your pole is.
You don't need to have poles on a sphere. This is arbitrary to decide whether you have poles or not. So if you decide to have 3 great circles on a sphere, this defines 3 equators.
No, you choose. The name equator is chosen.
So we're going to just arbitrarily choose one as an equator in order to just do a
You
mathematical
always choose
analysis.
One. Yes, that is the reduced 2 of the Euler identity. The 2 that you choose. You always do that. It's irreducible.
So you choose one is the equator. Then
yes,
that's arbitrary.
choose one.
It can be anyone.
Yeah. All that is important here is that on these spheres, you see 3 bold great circles. Do we agree to that?
Yes.
Yeah, we see 3 great circles. Yeah, bold ones.
My point is that any contiguous 2 great circles have 12 degrees of angle between them.
So
anyone adjacent, anyone that come like this, the angle, the finest angle that you can find is 12 degrees.
So from here, whoops, sorry.
Sorry, where's the angle measured?
We can arbitrarily pick any place, and we're going to say
any triangle that you take at the surface from the axe of a pole. It makes 12 degrees. And that divides the surface of the spheres into 120 equal parts.
Okay, so that's what you're measuring is the angle from the center, the ray
like
from the angle in the center to one point of the sphere, and the ray from the center of the sphere to another point on the surface, and you're measuring the angle at the center.
Yes, and the angle is 12 degrees.
Okay.
My point is that if you had projected this onto a plane, and we saw that the hexagon and the pentagon describe the whole inside of the stuff in the measurable way, you will see the largest common denominator between the two, that is 12 degrees.
Okay, I want to know where the 12 degrees is, because the easy one for me to see here is the 60 degrees. Each one, there's 60 degrees at each vertex of this triangle.
Okay, if you take the center, Steve, you see the center?
This is what is incorrect, Steve. The angle is not 60.
It's 60 degrees from each one of these vertexes.
It's 60 degrees if the triangle is on a flat plane.
But it's also 60 degrees even on a sphere.
The sum of the angles in a triangle on the surface of a sphere is not 180. This is spherical geometry. On a plane, if you go on a straight line, turn 90 degrees, then turn 90 degrees, then turn 90 degrees, then again 90 degrees, you go back to where you came from. If you do that on a sphere, you're not going back to where you came from.
Okay.
And that's the key. That's why
you have to be very careful when you go from a flat to spherical or to hyperbolic, but let's talk about spherical here. The sum of the angles is not the same.
Yes, that's why you measure from the center, Steve. The center of we're talking about the angles at the center of a sphere. The angles of opening of whatever goes and be projected at the surface.
So you're talking about getting into the center of the sphere, creating a point in the center
of the sphere. Look at that figure. You see that center, what you are showing.
Well,
you see the domain that is hatched there? You see part that is hatched. That is at the surface. But if you take any of the spokes that go to the surface of a sphere from the center.
Are you talking about that center right there?
Okay, let me explain to you with a vision, Steve. You see that sphere is a wheel, right? Is is a sphere. Imagine that you have spokes that go from the center to the surface,
So you have
defining,
radii. You have radii
yes,
from the
that go to
center of the sphere out towards the outside.
yes, yes.
Okay.
Between two radii that are contiguous, that are the next, from one to the next one, is 12 degrees. Any of the two.
Okay,
At the
so
center.
I don't understand that.
No, that's what it is. That's what I explained. That if you do it like that, you divide by 12 degrees at that point of the center. You have all of the radii. The one to the next is 12 degrees. At the surface, you're going to have 120 parts.
I'm just not getting it. So are you talking, you're not on the surface anymore. We're going to the center of the sphere.
Yes, to the surface. That's why it is scalable. It says that it doesn't change. It doesn't change whatever scale that you have. That is, it says the surface of a sphere is divided irreducibly to 12 to 120 parts.
Okay, well,
it doesn't change.
That's what we just read, was that from lowest common denominator goes to 120 parts, no matter how big or how small the sphere is. We read that in the book.
Yes.
That's the least common denominator.
Yes, that's my point. My point is that if you are at the center and you divide by 12 degrees, that way and that way, that's what you get at the surface. You have 120 sectors at the surface that are triangular sectors that increase the way if you inflate or you compress, it is still the same.
So you're saying
they are homomorphic.
Okay, homeomorphic. So you're saying that if on the surface of this sphere, that there's this intersection here, and that each of these irregular triangles that come off of this intersection each have a 12-degree vertex, a 12-degree variation.
Yes, at the center of it. If you go to the center, if you take that sector, that spherical sector, and you take the center, and then you have the three radii that come to the surface at those 3 points, the angle between any of the two is 12 degrees.
Okay.
So you're going to have 12 plus 12 plus 12, 36 degrees around.
Okay.
That's my point.
Okay. I'm going to share my screen for 1 second.
Go ahead.
That's okay with you guys?
Yeah, you'll interrupt my screen. That's perfect. Go ahead and interrupt.
Can you see it now?
Yes. But now you're going from the center of the sphere out to great circles on the outside.
Okay.
These aren't marked, but these are poles.
You're talking about the angle alpha, theta here.
Okay, is this a North Pole and is this a South Pole?
The angle ACB, Manu. Is that correct?
Yes. Yes.
Okay, got it. Because if we're talking about the surface of the sphere, and I'm going to share another one, which I put in the chat. I'm going to share this one.
It's very nice.
Can you, right?
I can see the one in the chat. You're still on the...
Okay, share that.
Yes, that would be beautiful, Fred, if you could get now to the center in dash and then project, see if we see it.
I can see it.
I don't know what you're referring to now, Manu.
No, I'm just saying that if you had that at the surface and you showed, I don't know, maybe you show the center of a sphere and then you have in dash the three radii that come to the 3 points of the thing at the surface.
Okay. That's not what I'm showing now. So let's focus. Now, if we're talking about the triangle on the surface of a sphere, the angles the sum of the angles does not add up to 180.
It's
It's
more,
larger.
yes.
It's
Yes.
more. And in the case of an equilateral triangle on a sphere, it shows here on the drawing. I don't know if it's because it's got 90 degree from the center, but it shows those angles at 90 degree at each vertex. I think it's general case for an equilateral triangle. Equilateral means triangle with the same each
Size, edges.
each
So you're
side
saying
has
that an
each side has
equilateral
the same length.
an equilateral triangle expressed on a sphere is going to have 3 times 90 degrees rather than 3 times 60 degrees
Correct.
because it's on a sphere.
Yes.
And does the
And do you know do you know why it's 3 times 90 degrees, Steve?
do I
It
know
is
why?
because any radius that comes and hit the surface of a sphere, it hits it at 90 degrees. If you take any radius that goes from the center of a sphere to the surface of a sphere, it's always at 90 degrees.
Yeah, but except
Right.
you just went interior. This is on the outside. This is on
I'm
the
just telling
exterior.
you,
He's
why.
he's referring to some sort of theorem that links the inside angles with the surface angle or something, but I don't know. I don't know which one it
Right.
is. Okay. So thank you for the clarification, Manu. That was that's useful now. Thank you very much.
Okay, Richard's got his hand up. Are we ready for Richard to interject, Manu? Are you ready to let Richard interject for a minute?
Yeah. Richard can go. It's open. That's why we are here.
Go for it, Richard. You're muted.
Yeah, okay. Well, I was going to the text and I was looking at the spherical triangle has 15 LCD units. So, and then it says if you take 15 by each face, so 15 times 1 times 8, you get your 120. So what I would like, if it's possible, to show the 15 LCDs in this spherical triangle. Can that be shown there?
We'd
Just
have to
like,
bisect each of those angles till we came up with the LCDs. But I think that's what it would be showing. That's what we're seeing when we go back to the picture. Fred, could you just take a second and throw that other? Go ahead.
Yeah, okay. So if we bisect in that spherical triangle, we'll end up with 15 LCDs. And then as I understand the text, there will be 8 of those spherical triangles. And so you multiply 15 times 8 and you get 120. Does that make sense? Is that correct?
It doesn't make sense to me because if you bisect this the one that's shown here, this is not the one from the book.
In the book.
But we can use it as a prop to see the inside of it on the surface. If you bisect the first angle, the second angle, and the third angle, and then if you bisect again, you get to 12, not to 15.
Well, that's why interesting. The text says you get to 15.
I don't see it in the text. Can you tell me? I'm going to share the text again. Change the text.
I'm happy to share the text.
It's okay, I got it.
Okay. See, the weird thing about your triangle that's in Fred, your triangle that's in the chat now, the blue triangle with the 90-degree angles, that's a quarter of a sphere. You're at a North Pole. You're at a North Pole, and you come off at 90 degrees off the North Pole, and you come down each side. You could do that 4 times.
Yes, but this scales whatever the size of the equilateral triangle that you put on the sphere, the property that the angles are 90 degrees at each vertex remain the same.
So I don't think that angle is 90 degrees on the 14-C LCD unit. I
No,
don't think that is 90 degrees.
it actually is because I
Except that
think that
there's more than four of them.
I think that's yeah, but I think that's an invariant property. Invariant
Well,
means doesn't change. It's a property attached to the type of
what's
triangle.
really cool is when I look at my screen right now, and I'm just going to do a screenshot so I can show you what I'm showing you, what I'm seeing, because that way everybody can see what I see, because I think we're getting to the bottom of what I don't understand. So I'm going to now share my screen, if I can get rid of some stuff, so that, and then I'm going to share this. So now you should be seeing the book over on your left-hand side. You should be seeing your sphere that you put in the chat on the right-hand side. And now, fortunately, when I took that screenshot, I can see your other sphere down there, Fred. That's really nice. So what I see in the blue sphere is that you can only do what you did 4 times in the northern hemisphere. That's 90-degree angles there at the top. They're 490 degrees, 4 times. 2 of them are 180, so 4 of them will be 360. So as soon as I put the red triangle on a sphere, it doesn't matter how many meridians or whatever those are called, latitude lines I come down. Every time I do a latitude line, I'm going to be at 90 degrees. Is that right?
I'm checking.
Do you have some
I'm checking if from the
and
angles.
while he's looking at it, then if there's 4 on the top, there'll be 4 on the bottom, and that's 8.
right?
And so then if I can get 15 LCDs inside each one of those triangles, then I
You
get,
can't. I don't think you can, Richard,
well,
because this is
yeah,
showing different
yeah,
triangles.
but hang on. It's going to help me then when we look at the section where she talks about this. This is sort of in the next page. It's 1411. And she talks about if we have,
What page? 1411?
yeah, so it's the next page.
All right, I'm going to just show that. So there's 1410, and now we're going to go to 1411. There you go.
Yeah, and then you get the text that's under that LCD of 31 great circles, which is should be above that, I think.
Well, here it is, 411, revealed in 31 great circle pattern.
Yeah, I know, but I'm looking for the text.
Oh, it's just above it.
No, this text then will be below it in
Okay,
terms
good.
of my
Very good.
my book.
Okay, good. Is that
Yeah,
important?
yeah. No, just a minute. So go down a little bit further. Okay, stop there. So this is what I've been looking at is the paragraph that starts with secondly. If we recombine the 120 units into 12 groups, then we get the pentagonal dodecahedron, and you get your 10 times 12 is 120. Then the next paragraph says, next we discover a few asymmetrical transformations. A spherical triangle of 15 LCD units incorporating a complete icosahedron triangle framed like a pinwheel is one face of the spherical octahedron. And that's what I think we're seeing up there. With this observation, we isolate the octahedron by looking at the pattern, so it's worth checking the arithmetic. Multiply 15 units per face, 15 times 1, then by 8 faces, you get 120. That's the one I'm trying to get my head around as to whether that spherical triangle can be divided into those 15 units. That's all.
Okay,
And
so
maybe that's not the right triangle to try that on, but
let's come back to what you're saying because I think you're on a good track, Richard. I just want to go back to something that came up for me, and that is that if we take the blue sphere and we put the 90-degree triangle on it, we're not using the icosahedron. We're using something completely different. And we can put, and what that triangle does is it covers 1/4 of the face of the sphere. And if we stack 4 of those together, we've stacked 2 of them together, we get 180 degrees. We stack 4 of them together, we get 360 degrees. So now if I stack those 4 triangles at 90 degrees, I get 4 of them. That makes 360. Now, if I put that at the bottom and come up from the bottom, that makes 720 degrees. I just thought I would say that. But what she's talking about is not that figure. She's talking about an icosahedron
Yes.
that has
okay.
3 great circles, not 2 great circles. Fred's
Yes.
blue picture has 2 great circles and an equator.
Yeah.
Yes, and I think I checked, you're correct. And Manu is correct also. The angles at the apex of an equilateral triangle at the surface of a sphere are related to the angle at the center of the ray that goes from the center to each of the apex. That is, if your triangle is not 1/8 of the surface of the sphere, then the angles are smaller than 90 degrees.
Exactly right.
Yes.
But what
And
Fred, what
I
Fred
checked
is
that.
saying, what Fred is saying is very fundamental because that is the fundamental of what we call intertransformability. Is that relation between the outer and the inner. Because that's what allow the flow of folding and unfolding. If you don't have that relationship, you have nothing. You have a disparate world. You don't have a structure. You don't have order. You have chaos.
And what you just did, Manu, is you just went from the outside of the sphere, represented in the red right angle triangle, 1/4 of the sphere. You just went from that paradigm down to the Fred's bottom paradigm, where we're coming from the center of the sphere, creating radii out to great circles on the outside. And
Yes.
so
Yes.
you just did
Because
this.
my assumption was always that every division goes through the center.
Yes,
I
there's
don't
a
talk about
relationship.
anything. Yes.
There's a relationship between the inner angle,
Yes.
it's not the inner angle, the angles at C, at the center of the sphere, of the rays going to the apex of the surface triangle, and the angles of the inner angle of the triangle. There's a relationship. You can calculate one from the other and vice versa.
Yes. Let me
So
share
we can
something that
to illustrate and to piggyback on our duality. I guess we've got a duality here between those 2 angles.
it is what is called duality in, if we agree on the term that duality means complementarity in the fulfillment of a certain function. I think we'll be fine all of it because we will always talk about duality as a principle. That's all. I'm saying that,
I don't want to reduce the understanding of duality that we had last
okay,
time with all the distinctions to something that's so restrictive. So, but
okay,
I can make the distinction between. I mean, I start to make a much better distinctions between the different types of duality since we
yeah,
looked at it, since Steve did the research on it. All right, I'm
okay.
complete on that. I'm happy with it. I
I
think
would like to put,
I'll be even more complete if I understood the 12 and the 15th divisions that Richard mentions from the text.
Me
Because
too.
this, I'm not sure I fully
Yeah.
understand.
Me
Yes.
too.
We can maybe
may I,
do just a minute. Um, I, for me anyway, now, if we work through those 4 diagrams on 1411, so on the first one, what they're getting at is that um, there's diamond faces we can see in the diagram.
I'm going to show those, Richard.
Yeah, okay.
So the first one is A, you're talking about,
Right.
right?
Yeah, and it's got diamonds.
Okay.
There's 30 diamonds. So 30 times 4 is 120. Then the next one shows pentagons, and you get that pentagonal dodecahedron, and you have 12 groups of 10, which is 120. And then the next one shows, which is the one I think I was looking
I
at.
think this is Fred's. This is Fred's 90-degree puppy. This shows a whole quarter of the sphere.
Yeah, could be. Yeah. And it's that one.
It's an octahedron. That's right, because it'd be the quarter of the sphere. So there'd be 4 on top and 4 on bottom. That's 8. That's an octahedron. So you should have 8 of these.
And this is where there's a spherical triangle of 15 LCD units incorporating a complete icosahedron. Then you get this 15 times 1, 1 being the face, times 8 equals your 120. So it's all these different ways it comes up with, I think what Manu talked about at the very beginning is to get a fairly simple way to understand how it always adds up to 120. So you can do it 10 times 12. You can do it
2 times 80.
Yeah, but you in here you can do it that where is it?
2 times 60.
Okay,
Yeah.
can I?
No, just one more second here. You do on the diamond one, you get it's 4 times 30, then it's 12 times 10, and then it's 15 times 8. And I don't know what, I haven't got to the D yet, but what is that one? Anyway, whatever it is, it's going to end up at 120. And this has been very helpful for me to be able to see what those 4 diagrams are all about. It's trying to show me, the reader, all the different ways I can get 120.
I get half of what you're saying, Richard. I think you're right on, and I get half of what you're saying.
Well, you should be getting 3/4. It's the fourth one that I haven't got yet.
But am I correct in saying that C down here is 90 degree? It's a 90-degree triangle. It's 1/4 of the sphere. That's why it's an octahedron, because there's 4 on top and 4 on bottom makes it 8. That's an octahedron. That's a spherical octahedron right there.
Yeah, and it looks like what I saw on that the diagram that Fred put up in that spherical triangle.
Yeah.
And in that there's 15 of these LCDs. And then 15 times 8 is 120.
So in other words, if I go through and count up within this gray area here, I'm going to count 120 triangles in here. Is that what I'm going to count?
No, you're going to count 15.
Well,
Then
1, 2, 3, 4, 5,
then you
6.
have 8. Then you have 8 of those gray triangle.
Right.
And then 8 times 15 is 120. Thank you, Richard. Very appreciate your explanation there.
Well, I got half of it.
Okay. Look at let me share my screen.
I wanted to share something first, unless you want to add to Richard, Fred, which I'll leave you.
I would like to add to Richard, if that's okay with you.
Okay, that's good. Yes.
Thank you both.
Thank you, Manu. Share. Are you seeing something?
Yes. Beautiful thing.
Okay. Okay, that's the same as what was great on Richard's explanation. Now, if you take this triangle, there's 8 of them to cover the whole surface of the sphere, and each
Right.
of them can be divided into 15
Just by
portions.
bisecting each of
Yes,
the sides and continue to
yes,
bisect until
until you count.
8 times 15 is how
And
much?
Yeah.
120.
Exact.
So that's all I wanted to say. Manu is yours. Thank you, Richard. I
Okay.
very much appreciate your insight on that.
All right. I want to show my finger.
okay, well, I'm gonna stop sharing. I think
Yeah.
it's me that's sharing.
Yeah.
No, it's
If
me.
you
Stop
pin
sharing.
me, you see this beautiful thing that I built with Steve. Steve has one too.
Yes, I
It
do have
has,
one.
yes. This is a kind of description, is an approximation of a sphere that has 20 equilateral triangles and 12 pentagonal faces.
Pentagonal faces. Yep, 12. This is a an icosahedodecahedron. That's what this
Okay,
is.
right. But what I'm going to say is what it is important in all of this game. If you look at what I'm doing, Lee, I really want you to look at this.
All we can see is your chin, Lee.
Lee,
You
are you
need a
seeing
black,
me?
I
you need a
think
black t-shirt.
Lee is dozing.
Well, she can see it.
And I know she's dozing, though. We've had a long day. Hey, Lee, are you here? They're talking to you. I know you.
Lee, I just want you to see this.
Oh, okay.
Yes, this is for you. You see this guy here that we play with is an approximation of a sphere. You see it? It's like a ball.
Yeah.
These are faces that I've numbered of these triangles that are here. There are 20 of those, and the gaps that are pentagonal at the surface are 12 of them. 1, 2, 3, 4, 5, 6 on top here. 1, 2, 3, 4, 5, 6. Now, this is what is important. Our sphere is something like this that can twist, that can turn, that can do things. Now, I'm holding face 2 and 9. 2 and 9. Look at what I do. You see this? Something comes here, I push it, and I do this. Do you see that it's a little bit twisted?
Yes.
It is changing. I can also twist this guy onto this one. Do you see that?
Yeah.
Yes. It takes different shapes. And what we're talking about here is the play of this thing. And in doing that, you can identify things of significance or new things that were not identified before. That's all he has said. It has reduced, the whole of that study was to reduce the surface that you can touch like this, that you can materialize into something like the one that I put here. And we've gone to the minimum possible that you can have of a triangle of a surface. And all of these are bonded, either single bonded here, all of this, the sphere here is the most expanded because everything is on something like a single bond. You see one vertex coming and linking to the other vertex is like a gas, is the most expanded. That's why we say the sphere is the most expanded, or what you call that is finite. And this guy spent his time folding and unfolding to contract, and to expand. Because you fall to a certain limit where you can no more fall. Given where you started, there is a way to fall that can allow you to go to have everything stuck on the other. That is the jitterbox. It was unfolding everything. The jitterbox here is represented. You know that these pentagons, there are 12 of them. So imagine that you take from the center, ready that come and hit the pentagon at its circle, at its center. Those are the 12 degrees, the 12 dimensions that Bucky talked about. That's why you have 12 in the description of the vector equilibrium. And for some fun here, you see that these vertices come at the center of the voids, which are the pentagon here on my. It is a convention. So it is unstable because the vertex is supported by something that falls. The triangle here will not fall. If you take the radii that comes to the surface of a triangle here, there are 20 of them. So you're always having that relationship of 12 and 20, which is also the relationship of 5 and 6. That is at play in our direction. And in doing this simple exercise of folding and unfolding, you accidentally identify something that we didn't know before. All we know is that it goes from this most expanded, is the principle, to the least expanded, that is to the most concentrated. And everything we know in life goes like that. In chemistry, we know about concentration and dilution. In mechanics, we know about inflation and compression. In whatever language that you have, you can speak like that and build things that make sense in the fulfillment of a function. And we hope what we call, what the design that Becky imagined is that you could actually, through education and through decision, anticipate the outcome. That is, you build something today for a very well-defined outcome. That's what we call anticipatory design. There's a word for it, Steve. What was the word that we usually use with Susan? It's called when you do something with the result in mind.
I don't remember the word, but I do remember the reference.
Yes, there was a word for it. It starts with P.
What's your definition?
That is, you do anticipatory design. That is, if you're doing something, you don't do it like haphazardly.
Yeah. Give me the word. Please repeat the wording of the definition as you said it.
I say anticipatory design. What Becky meant by that, there's another word that he uses to describe, is that we do things today for outcomes that we know well defined. So all our action.
We do things for anticipation.
Yes.
We don't do them for prediction.
Yes, for anticipation, because we want to know, before it was, hey, there's expectation. So there's something and then you are expectation. But here he uses the word anticipation. We know where we're going to.
We can anticipate it. I mean, this is really intriguing for me because it helps understand the difference between going for something that's predictable and going for something that's anticipatory.
Yes.
And there's a difference.
Yes.
The word is dimension.
Yes, but there was another word. I'll find it that he uses.
We had the same conversation last week.
And so this is the
I
difference
interrupted you, Richard.
between,
Sorry.
yeah, this is the difference between design science and pure science.
It's also what we talked about last week in terms of causal and non-causal systems.
Yeah.
Non-causal systems depend on future activities, and causal systems depend. Non-causal are present and future activities, where causal are present and past activities. And anytime there's a future activity that hasn't anticipated, it's non-causal and it's anticipatory, like
Okay.
weather, like the weather. Because
Yes.
I asked AI for an example of non-causal systems, and they said the weather's a good example of a non-causal system.
Yes.
Yeah. And in my field, which is kind of interesting, is that um, experiencing something to do with suicide is non-causal. And yet what the field, the science is trying to do is to make it predictable. So it keeps trying to find a precise prediction of the elements that would add up to somebody being at risk, and it doesn't work.
Mm-hmm.
And if they would work on the anticipatory part, or work on the probabilistic part, they wouldn't get so caught up with trying to precisely predict something and to actually try and categorize it into boxes called high, medium, and low risk that have no real significance in the reality of someone's life,
And could actually
their
be
living
distracting.
experience.
And
And
could
it,
be
yes,
distracting.
and it will distract you and it'll make you do things that that don't work. And in doing that, then instead of realizing you're doing something that's incorrect, you'll blame the victim and
Right.
say they didn't follow your instructions correctly.
But Fred
So,
points out something very important, Richard. There's no
yeah,
money in prevention.
yeah, right.
That's true. That
Oh
is
boy.
true. That is true. We get into ethics here. There is no money in prevention. If you prevent, there's no case to justify somebody.
Right. Let's don't
Yeah.
stop cancer. Let's just
Which
treat the
is
symptoms.
which is why we evolve from crisis to crisis just in the nick of time.
Just in the
Yeah.
nick of time.
And then we're back to critical path.
Yeah.
Yes. At the nick of time, Bucky recognized that very, very well.
Let's
Is
see if
that
It's
we
in
can
the it's in
let-
it's in the introduction of critical path. If we're going to make it or not,
and that
it
come
will
to
it,
that
it
come
will
that
it will
come to
be
a,
in the nick of time.
that will come to a point. Do we accept that change come because of a few brave, or is it going to be the mass that changes? I think, me personally, is a few brave.
Yeah, and when you get into that kind of dialogue, then you're also making a distinction between linear and nonlinear. And
Yes.
it's the nonlinear where you can have a speck of sand that can trigger a huge sort of collapse or a huge positive. And you don't need what we often think of is that we have to have critical mass before something will change. Well, that's in a linear sense, that's probably true. In a nonlinear sense,
yeah.
it's not true.
Yeah, in a
Uh,
causal system, it's true. But in an anticipatory system or non-causal system, it's not true because
yeah.
the future can carry much more weight than the past.
Well, the other part of this causal and non-causal is the causal works off of proportional cause and effect,
Right.
and non-causal works off disproportional cause and effect.
And
Uh,
sometimes causal is linear and anticipatory is nonlinear, and I think one way to look at it is it's four-dimensional. It becomes a hypergraph where every element in the system has as much potential to affect the future as any other element, whether it happens in the past or in the future.
Yes.
It's a four-dimensional perspective. Richard, Fred, you have your hand up.
Love it.
Yes, thank you. I completely agree with Richard, and I think to rebound on what Manu just said, I think change starts at one point, that is one individual or small group that gets an idea, to put an example on the table, and then it evolves in time, or it propagates in time, and this is nonlinear. The buildup of critical mass, as Richard pointed out, this is completely nonlinear, and it builds up invisible until there's an inflection point and things change, and things change brutally. When I mean brutally, it's in an instant compared to the time needed for the buildup. And this is also why we usually observe evolution as being catastrophic. Catastrophic is another word for brutal, as I just explained it, meaning we evolve within a frame slowly, but incrementally, until we evolve brutally, and then we repeat. And when I say I go down like this, it could be going up. It doesn't matter the direction. What matters is there's a
And in
huge.
catastrophic literature, there's what I've read is there's two kinds. One is called a cusp, like on the edge of a wave, and you either fall back or you fall over. And the other is the fold, which has to do with that slow build up, build up, build up, build up until the straw breaks the camel's back. But it's
Yes,
this build up and build up and build up of a pressure or stress or whatever it might be.
I entirely agree. That's correct.
So,
Thank you.
so socially, why do we need democracy then?
Why do
Why do we
we?
need what?
Why do we need democracy?
The what?
You don't.
Yeah, but what's going on though, it goes back to what um, Manu has talked about at the beginning of our sessions for quite a long time in terms of what do I want to get out of all this, is that at some point I want to be able to get out what would be the applied sort of value of whatever we're learning about. How can we take the knowledge and convert it into something that's practical or applied and works for 100% of humanity, but to keep turning things into some kind of applied practice or applied application.
Okay.
Yeah.
But I also mean that more generally, I don't know, maybe it makes your life more difficult. Because spending time here, you learn to see things that others don't see.
Mm-hmm.
And, and it is imperceptible, but it is real. And then you
Yes.
come out, at your place, you're talking to somebody, you think that is evident, it's not.
It's because you people, Kelly was like this, Richard is like this, and Manu is like this. You people are putting your desires at 180 degree or at 0 degree, straight in front of you. You do not let precision takes
Take
happening.
place.
You do not leave space for precision. That is, you're putting your goals ahead of you because you want application. You say, I want to learn something and then I want to apply it. And Kelly was really pissing me off every time he said, I need an application for that, otherwise it's useless. Well, no, it's not. It's not useless. The accumulation of knowledge is the accumulation of knowledge. What you're going to do with it, that's another completely different
Right.
topic. But that's my opinion.
Is your background there, Fred? You see your background. That's the application of knowledge. You see the bright coming down and accumulating. Do you see that? Maybe you don't see your background. On
Because
your
of my
picture here, I see stars.
Yeah.
my
And then,
background.
yeah. And then I see at the surface is brighter. So some stars are falling behind you and accumulating, illuminating, without even you been perceiving them.
I
Do you
don't
get
know.
me? Or my
I don't see
humor is
I don't see
is
that background.
morbid.
You're the one that sees it.
I'm seeing it.
It's
Okay,
in the
we're
back.
going to take just a minute and finish reading this section, and then maybe we can. And
Yes.
Richard took us through, but I think it might be good to go ahead and read, Richard, since you started. If you want to read that next we discover, and just go ahead and finish off this section. There's only 2 paragraphs here. You want to do that?
Yeah, okay. I'm just trying to locate it in my text here, but
Okay.
okay. Next, we discover a few asymmetrical transformations. A spherical triangle of 15 LCD units incorporating a complete icosahedron triangle radially framed like a pinwheel by 9 extra LCDs is one face of the spherical octahedron. With this observation, we isolate the octahedron face just by looking at the pattern, so it's worth checking the arithmetic. Multiply 15 units per face by 8 faces to get 120, or the whole system.
Yeah.
Now then, figure 1411C shows that this skew relationship again reminiscent of the jitterbug transformation. And lastly, we observe the edges of a spherical vector equilibrium. At first, this seems to present a contradiction given the unsynchronized relationship of the 25 dash and the 31 dash great circle patterns. However, the VE's 4 great circles are included among the 31 icosahedral equators, although asymmetrically positioned with respect to its vertices, 1411D. We now recall from Chapter 11 that it was possible for all the faces of an octahedron to be aligned with 8 of the icosahedron's 20, figure 11.5. This skew correspondence, which defined the S module, shows how a set of 4 out of 10 circles generated by icosahedron faces will be correctly situated to create the spherical VE. The number of different polyhedra hiding within the 31 great circles reemphasizes the existence of significant relationships between the out-of-phase icosahedral family and the IVM group.
Okay, so that's nice to know that what we're doing is figuring out how to anticipate everything all at once.
Yes. And you remember what figure 11.5 was, that? Was the truncation of the icosahedron.
Yeah. Let's see here.
The truncation of the octahedron, I mean. To get
Okay, we
the
can
wrong.
read this. We can read this next part, and we've only got 1 more paragraph to go, and we're done with this section. So I'm excited about that. Does anybody else want to read, or shall I read?
I can read.
Okay,
If you
go
can
ahead,
support
Manu.
my horrible accent. Okay, the 25 great circles. V is 25 great circle. The intertransformability displayed by vector equilibrium's least common denominator is straightforward. In contrast to the skew relationships demonstrated above, groups of 4 units create diamond face exactly centered over each VE vertex, thereby defining the 12 faces of its dual, the rhombic dodecahedron. Figure 1412A, 6 LCD triangles come together to create octahedral faces. Figure 1412B. While the cube 6 square each consists of 8 asymmetrical units, figure 1412C, and the spherical tetrahedron uses a dozen of LCDs per face, distributing the 48 units among the only 4 faces, 1412D.
And here are all
This group,
those,
yes,
here are all the pictures right here. And then we finally read the last paragraph. Go ahead.
this brief look at various grouping of LCD units shows how great circle diagrams provide a new way to classify certain polyhedral characteristics and thereby discover shared symmetries between systems.
Cool.
Wow. I
Well,
think that's what I try to highlight to leave with this.
I saw that.
Yes.
cool. I actually got something out of that. Any other comments before we do our takeaways? Any other things we noticed in the last little thing? I just don't think it would be helpful to start reading our next section at this point. Cool. So, Richard, thanks for your cranking down on that 1411 and reading through ahead to catch up and to put it all together. How are you feeling and what are your takeaways tonight?
Well, I'm feeling pretty good. And again, I think the big takeaway is what we've all said from time to time about the importance of well, number one, being able to go beyond reading something all by yourself and trying to um, discern something new or learning or something applied out of that, um, compared to being able to do it in dialogue with others. Um, and for me, there's an interesting comparison, I think, between the dialogue with others in whether or not you're sitting in a room, let's say, in a row or in a row, like a row of three or four or five rows of participants, or you're sitting in a great circle or circled in a room, and the difference in terms of how one can learn in those two different kinds of spaces. Um, and the other one is the demonstrate or the importance of being able to take whatever the acquired knowledge is occurring and turn it into some kind of if you want application or hands-on, whether it's doing what Manu does an awful lot of, and that is putting together models or that sort of thing. And it really becomes helpful in terms of understanding um, if you want, the academics or the abstract of what we're talking about. Um, and then I think the other part that's really important is to take that body of knowledge that one can acquire over time and figure out ways you can apply it. And so what I take away is a big reinforcement for me that again is something that is not happening in my field. But when students in my field enter, they have to take a research course, which really speaks to the knowledge generation, the bench research sort of part of building knowledge. Then there's others who take a course voluntarily. They select it, but it has to do with evaluating what somebody has put into play. But there's a big gap in between in terms of student interest. And I found years ago that the gap can be filled with something that's called social research and development, social R&D, which is a transformation from industrial R&D over into what is called social R&D. And social R&D is where you're taking the knowledge and you're turning it into a practical application. Um, and people in my field want to do that because they want to save the world. So they're always looking for practical sort of ways to be helpful, either on a sort of a clinical scale or a large change scale, macro scale. And so that to me is one of my takeaways is the reinforcement of the importance of that in between kind of research where you take something that is known and you turn it into something that can be practical or useful for somebody. Um, and so I'm reinforced in that kind of belief, and I'm also distressed that in my field, the idea of a social R&D research course is still not commonplace. So um, it's really ironic that the people who come into my kind of discipline want to change the world, and nobody teaches them a course that helps them figure out how you can convert something um, of that bench knowledge that Fred was talking about into something that can be used as useful. And of course, that comes from all kinds of fields, trying to turn the knowledge into something that is a better treatment or a better application or a better way to build something. So that's my takeaway. Um, and Fred, how are you feeling? What's your takeaway?
You're on mute, Fred. You're muted, Fred.
Sorry about that. I was saying I'm going to keep working at 90 degree. That is, you figure out how to use the knowledge. I'll I'll keep studying and discovering and be curious about things that interest me. For instance, this week working with Susskind, I found out that light does not move. It when it is emitted, it is emitted at the same time at the source and the arrival place, wherever the arrival place is. And the reason for that is that there is no clock on photons because the clock is not moving. And if the clock is not moving, there cannot be movement. So relative to the light is emitted and received simultaneously. And this is the one and only exception of our non-simultaneous universe. But the consequences of that are staggering. For instance, and then suddenly the staggering consequence eludes me. I'll keep going and maybe it comes back to me. Now you're going to be very hungry for that one. This was a very pleasant call. And I would like to thank Manu for the diligence he has into preparing, because when I see intertransformability appearing the next page, I know Manu has read it prior to the call. Otherwise, it would not have showed up. So I would like to convey my thanks and gratefulness for that, and also my thanks for spending the time to explain his ideas and how he sees things and his explanations. Uh, uh, in spite of my insistence into understanding, he's very patiently explain things and to my benefit. So very grateful for that. Very grateful for Richard for sharing his insights. That was wonderful, even unusual insights into figuring out how the spheres are subdivided, the 120 and all that, but also and mostly his insights into his own domain, which is sort of foreign to me, but which is very interesting and beams a flashlight from a different angle and makes it very interesting. And I'm desperate into trying to figure out what I was about to say. I don't have a note made about this deep and profound insight that I had this week about the light that's not moving, but I can't figure it out. So I'll pass it on, and if it comes back to me, I'll let you know. I'll share with you. So thank you all. Lee, how are you feeling today, and what is your takeaway? And please unmute yourself.
Well, I went through hell. I had to go all the way back to my apartment to get eye drops. and they burned horribly. You speaking of light, standing still, the screen when Steve is putting it on the TV or even on my screen on my phone is so bright. I can't handle it. And so I'm covering my eyes so I can have more darkness to see your faces. At least you guys are not bright, and except for possibly Manu. Manu's got a white shirt on, and it's a little too bright for me right now. Um, I understood an awful lot of what was being said, even though you couldn't see that I was still there. Um, I was, and I liked being able to review. Steve, don't yawn. um, but the review and Manu's simple little diagram that he uses constantly, and Steve has got his own now, really makes so much sense to me in all that I have been learning. And I am very, very grateful for all that all of you have taught me. There's still more for me to learn, and I hope I can continue to learn. Manu, have you spoken? What? How are you doing? You're muted, so please turn off your or turn on your mute. Yeah, and let me know how you feel and what you got out of the conversations today.
I feel good. It's sunny, it's almost to 7 here, quarter to 7, and it's nice. It was a nice call. It was really good. My takeaway is this one, is that I know we are always in between something. We live in between. And then we've learned here that we can be reached from the micro or from the macro. And we also learn here that the patterns that we identify there is the macro image reaching us. The micro image is those LCDs, is the mites. I can also account from there. Therefore, I have no reason why I shouldn't try to use that twin information that I get to try to do something that is useful. And I'm thankful for that. That is my biggest takeaway, is that we are. The second takeaway is what we discussed about a few brave men and women. Let's be those few brave men and women. By our ethics, by our approach to things, and by our dedication to always try to understand and always try to make use of what we understand to the betterment of the many that we can. So that's my biggest takeaway. Otherwise, I'm grateful. And I envy Anne, who's preparing for the Chinese New Year. See, Fred too. I don't know what they're going to do, but hey, I would like to visit one of the Chinese family around here and see what they are doing for the New Year. Richard,
I'm going
how
to
you
spend
been?
I'm going to spend a new year with Leonard Susskind.
Wow,
Well,
that's
I
cool.
sure like the new year being a horse. I'm really particular for horses.
Yeah. And Richard B.
Richard's already gone. I think I'm the guy left.
Okay, Steve, how do you feel? What do you take away?
Listen, I'm very excited about tonight. I was a little bit distressed because I spent a couple years ago figuring out the 720 degrees. And tonight, when Manu said that a sphere had 720 degrees, and I'm going, now, wait a minute, how come a sphere has 720 degrees? But then we went to the cube octahedron, to the spherical cube octahedron, and there it is, 360 degrees on top and 360 degrees on the bottom makes 720. What I suddenly saw was a coin. One side is 360 degrees, turn the coin over, the other side is 360 degrees, and then all I got to do is pump air into it, and I have a sphere. And I'm happy with 720 degrees in a sphere. It's just a coin, an inflated coin. That was cool. So that came to me. I'm really delighted that Richard had his epiphany and started breaking down his understanding there of those figures for 1411 and 1412. That was huge for me. I don't get it all, but I'm getting some of it. And the big epiphany for me, the reason why I'm excited that I can leave this without beating myself up, is that this is the vector equilibrium with 31 great circles that manifest all of these different polyhedral energies. So it really is everything all at once. When I came to that, and I'm looking at all these great circles, now I have total peace, because those circles just everything all at once. And if I want to understand part of it and ponder it, I can do it. But in the meantime, it's everything all at once. And I'm big on everything all at once. I like everything all at once. I'm really excited tonight that Manu, if I may say, when you got questions from Fred and me about what you were saying, you slowed down and allowed us to pursue the questions and to come to the answers. I took a course in transformational grammar and syntax. That was in my 6th year at university. and it was amazing because I discovered that everybody has to come to something in their own terms. That I can sit and give you a map and give you the words, and you can't get there with my words and my map. You've got to create your own map and your own words. And if we're lucky, you'll use a lot of my words, but that's only luck, because you may use completely different words to get there. And that's where I like all the fact that, hey, it's got to be true. It has a bunch of neat diagrams and a bunch of triangles in it. If there's some metaphor in there that I relate to, I'm relating to. I'm jealous, Fred, because that Leonard Susskind video about the photon having no time. I've watched other videos. That one came up, and I emailed it to myself to make sure I watched it in the future. And I'm really pissed now because you saw that and I didn't. I've seen a different one though, and it's really a good one. It's about a rock is trapped light. And
Yeah, I've seen that one.
Did you see that one too? Oh, you
I did not
saved
watch
it?
it. I did not watch it.
That's the one I watched. And
Okay.
it's really cool because it has a bunch of neat triangles in it. And no, it has a bunch of tori in it. It has a bunch of toruses in it. And it's really exciting. What?
It's not Susskind, is it?
No, it's not Susskind. But I'm going to go watch Susskind, but I'll send out this one on Matter is Light. It's really good too. It talks about.
I have it open. I have it open in my browser. It's
Okay, good.
I'm
You know what's
doing
really
something and
cool?
watch it at the same time.
So all is about the density of tori, Steve.
The density of what?
Tori.
Of tori.
Everything
Exactly right.
it's about the density of it.
Everything's the density of a torus. It's all there. Sound, whether it's a sound wave or a light wave or a water wave or an air wave or an electromagnetic wave, it's all about the torus. And tori have angular momentum, which is very exciting to me.
Can I spice it a little bit, Steve?
Go ahead.
You, if you permit. If you have 12 people sitting around in a circle,
Yeah.
and each half is touching the other through the elbow.
Okay.
Each elbow. Who touched first? Is there time?
Yeah, I got you.
Everybody's touched.
Everybody's touching. So Anyway, so I had a really good time that I'm going to go to bed thinking tonight it's everything all at once. I'm a happy guy. And isn't it cool that we can hang out with each other, and when we hang up, we're going to go hang out with Leonard Susskind. I mean, what a day we live in. Really? It's so amazing.
We have to notice that when Joe is not there, everything's so pleasant. We don't yell at each other.
That's right. Okay.
Okay, can I share something more?
Shoot, yes. What the heck?
About Susskind, because I did not find my corollary, and I'm very frustrated about that, but I want to share that. Susskind says that one of the hypotheses is that the universe is a hologram, and he says his ideas are most likely it is. And what is a hologram? A hologram is a 2D surface, and from that surface, it's projecting and creates time and a 3D space that we are used to. But it's all an illusion. Everything is in 2D, and I felt vindicated.
Yeah. I see. Good.
That I understand 2D, but not 3D.
And I've heard that before. I think I started that Susskind video, and the idea is it's not only 2D surface creating a 3D, it's multiple dimensions coming off that 2D. It's multiple dimensions.
Well, who loves between the cartoons that we used to have in our youth, the cartoon printed of the characters playing the thing, and the movies today, which one is better? I prefer my cartoons. I really had a library. When I was a kid, I had a library of cartoons, and I developed an exchange. To be truthful, I don't know how I had cartoons, the thing, but I happened to be aware of everything that was appearing in the market. And there was I don't know, I exchanged things, all things we knew, and my library was just growing. It means that there was more coming in than going out. And I became a reference. I don't know how, but those are skills. If you're watching all the 4D or whatever, all the avatars that are being created today, you're never going to have that skill of creating an exchange. It is an experience. I prefer it.
Thank you for posting your book in the Richard, for posting your book in the chat. We'll see you all soon.
Thank you,
All
Richard.
right, thank you very much.
Bye-bye, everyone.
Just hold on. I want to copy the chat.